So where to start? So remember last time we talked about the pro-nilpotent completion of G, right? So you have the lower central series, gamma 1 of G is G, and gamma k plus 1 of G is equal to the commutators of G and gamma k of G. And then the idea is you could take the product of all the G, gamma k of G, and you're looking for elements in this where each element shifts down to the next element in the sequence, right? So one way you could say that is you could take the map to G mod gamma k of G, the product over all k, and I could do 1 minus the shift. Right? Where the shift is, it takes G2, G3, etc., right? Down to G2, G3 inverse, G3, oops, guess I should write it the other way. G3 inverse, G2, G3 inverse, all the way up. And the kernel of that is the inverse limit of G mod gamma k of G, or what we call G hat. Right?
Is this my homomorphism?
Is it a homomorphism? Ramon, do you remember? Is that a homomorphism in general? I think it is. Yeah.
This must be epimorphism, right?
It will. This, in fact, this will always be an epimorphism. In fact, that's right. That's not obvious. It's an epimorphism. But it is. Lim 1 is always, yeah, the co-kernel of such a map is called lim 1. In this case, it's always 0. So, right. So the example we looked at last time was, suppose you take u, t, and say u squared is trivial, and ut, u inverse is t inverse, right? And then we commented on, if you kill t, you just get the group generated by U, which has order 2, and T generates a normal subgroup, so you get this normal subgroup Z, and it splits. So you get a semi-direct product. And then we showed that if you take G mod gamma k of G, you get Z mod 2 to the k minus 1, semi-direct product Z2. And if you take the inverse limit of this Z mod 2 to the k minus 1, you get the two-adic integers. So in fact, G hat is the two-adic integers semi-direct product Z2, where this is the two adics. Just as one concrete example. Okay? So typically it's a huge group. Now, we use that to define transfinite Milnor invariants. So given a link L in S3, we have a map from the free group to pi, which I'll use to denote pi 1 of the exterior of the link, right? The compact complement of the link, just given by taking exi to a meridian. If this is a not ki, I have a base point, I choose a path out, and I take that curve suitably oriented, I guess it's the other way. And that's xi. And then we talked about the mu bar invariants of L, and these are uniformly 0 if and only if f hat, this induces an isomorphism, f hat to pi hat. Right? And so using that, we said, well, okay, so if mu bar of L is uniformly 0, then there exists a map from the exterior of L, well, to k pi hat 1, but k pi hat 1 is the same as k f hat 1 by this isomorphism. And that takes L cross S1 to a wedge of circles contained in here by just projection onto the meridians, and therefore you get an extension S3 into this space k f hat 1 union over a wedge of circles with a wedge of disks. And that's what we call k omega. Okay? So we get an element called theta omega of L in pi 3 of k and k omega. And that's what we call the first transfinite. We call the first transfinite Milnor invariant. Okay. So then we talked about a theorem by Roman and I that said that pi 3 of k omega is uncountable. It's huge. It's somehow too big in a sense. It'd be nice if it were countable. It might have a better chance of being realizable. But it's huge. We prove it's huge. It's a big. This is really hard. This is not a trivial thing to prove. We're writing it up now. The proof involves a comparison. Basically, a comparison between the nilpotent. You can, given a group, you can with a presentation, you can construct a space much like this one. So you could start for instance, with a lamplighter group and use that. And well, what we do is that doesn't work. But if you take the lamplighter group and you embed it in a finitely presented group, you can actually do some sort of a complicated comparison between k omega and some space you get from that. And using lots of very sophisticated tools in homotopy theory, one is able, with some work, to see that one can actually compute that's uncountable. So you compare this space to another space using a slightly more tame group. This very nice automata group, the lamplighter group. Now, now it's a fact which I'll talk about a little bit later that I've mentioned in the colloquium, is that if L is concordant to L prime, then the exterior of L is homology cobordant. To the exterior of L prime. So that just means that there's a cobordism between those two manifolds, which is a product on the boundary, which has the homology of a product, right? And this is just Alexander duality. The manifold you're removing has the homology of a product. You're moving an S1 cross I. And by Alexander duality, the complement the exterior has the same. So this is not a hard fact to see. It was first observed, I think, as a systematic approach to understanding concordance by Capel and Shanison. And furthermore, well, I'll mention this point a little later. But so somehow the question comes up, just to try to vaguely remind you of what the motivation for that point was. The realization techniques that worked for the finite invariants were you'd make it transverse, make the map transverse to the center points, and you pull it back, and it gives you a collection of one manifolds. But those one manifolds may not be connected. The inverse image of a point may not be connected, and you have to connect them up. But the key thing is, if this were the nilpotent group, F mod gamma k of F, then the exterior of that, you can easily show that the exterior of those of the link you get by pulling things back maps onto F mod gamma k of F, and that allows one to actually do the process of connecting up the components without changing the homotopy class. But this group is uncountable, and that fails. So what you might hope is you can now take a link, the link you get that way, and you can change the link by some homology cobordism and maybe make it closer to being onto. You can't make it onto because this is an uncountable group. Maybe you can make it onto enough to contain all the elements you might want to be able to connect up your components again. Turns out you can't, but nonetheless, it's a great question and a great idea, and it motivates this question: how does the group of a three-manifold change under homology cobordism? And so that's going to motivate now a lengthy discussion about an idea. This question was in some sense answered by Jerry Levine. And let's talk a little bit about what he did. So this is something which, this is Levine's, this is Jerry Levine's algebraic closure of groups. So we're going to take a side trip here and discuss this in some detail. So just a little interesting group theory for a while, and then we'll come back and see about its relevance to everything we're talking about. So a group G is algebraically closed if given any finite system of equations y1 equals g1 times c1, and I'm going to write c1 y1 through yk. I'll explain what that means in a second. I'm going to push this up a little bit down to yk equals gk c1 to y1 yk. So when I write that system of equations, g1 through gk are elements in G, and c1 through ck are words in the yi's, which actually lie in the commutator subgroup of the free group on y1 through yk, right? If you like, they lie in the free commutator subgroup of the free group here, right? Okay. So given any system of equations like that, there exists a unique, and this is the key word. This is different from other notions of algebraic closure group theorists often study. There exists a unique solution in G. So, so let me just state that in a slightly different way to make it kind of clear what that's saying. I have G, and I can form a new group from G. I can take the free group on these variables, these indeterminants, y1 through yk, and then I can mod out by the relations yi equals gi ci. I equals 1 through k. And the key thing is that that splits. That is, there always exists a unique, if we call that phi, there always exists a unique phi bar. Like this. That's what it means to be algebraically closed. I can find that I can set the yi's equal to elements in the group in a unique way such that all of these equations hold. Okay? Let me give you some examples. G abelian implies G is closed. I'll just call it closed. I won't write algebraically closed all the time. Just closed, right? Why? Well, if I have an abelian group, then if I put in any value for the yi's, these terms will vanish. They're commutators. So clearly, yi equals gi is the only possible solution, right? I have unique solution. Yi equals gi, right? So abelian groups are algebraically closed. Now I'm not going to prove this, but the idea of the proof isn't so hard. Okay? Suppose I have a subgroup. We'll call it A, and A is contained in the center of G. Right? So those are all the elements, of course, which commute with every other element in G. And so in particular, the elements A is itself an abelian subgroup. And now I take the, suppose A is contained in the center of G, and I take A in the center of G, A to G, to G mod A. Okay? And then if G mod A is closed, so I have a central extension of G mod A. If G mod A is closed, then G is closed. So central extensions of closed groups are closed. Okay? And you can kind of imagine maybe quickly on your own how you might go about trying to solve a system of equations like that. It's not so hard, right? I would take a system of equations and I'd push it down into G mod A, and that has a solution. And then I'd lift that solution to something in G, and unfortunately it wouldn't be a solution anymore. Right? Take that, whatever the yi equals HIR, I'd lift to some HI tilde, and they're not a solution. But I'll do a change of variables, right? I'll stick in now xi, if these are, say, elements h1 through hk, whose images are solutions here, I'll take xi hi, and I'll stick it in for yi. And then if I can, now I have some sort of a system of equations. It doesn't quite look like that, but it's some sort of a system of equations which has a trivial solution here. So then you play around with that, the form of those equations, and you show that it's equivalent in some way in the sense that it has the same solution set as some system of equations over G which has this form. And then you have a system of equations over G which has a trivial solution in here, and therefore you look back at what the solution is here. Now in the process of doing that, there's all sorts of conjugating you have to do. But the conjugation acts trivially on A, and you see, and when you really write that all out what that means, it turns out you get a very simple system of equations of this form over A. And that will have a solution because A is abelian. So, it's not so hard to prove this. I'm not going to go through the proof, but it's not so terribly hard. It's a very nice argument. And that has a corollary, of course, that nilpotent groups, all nilpotent groups are closed. Nilpotent groups are closed. Let's do a characterization. Let's talk about a characterization of non-uniqueness, or let's say a uniqueness of solutions. Let's write it that way. All right, let's talk about a characterization of uniqueness of solutions. And this is a theorem. Again, it's Levene. Everything is Levene. All of this is due to Levene. So if, let's see, there is a subgroup in finitely generated, say by some G1 through GK, normal in G, such that N equals Gn if and only if there exists a system of equations over G with more than one solution. Right? So that somehow completely characterizes this idea of uniqueness of solutions. So you can kind of imagine how that might work too. I can take these generators, these normal generators, G1 through, right? That is, this is the smallest normal subgroup containing G1 through GK. So I take the G1 through GK and I write it as products of conjugates of commutators of elements in G with the elements GI. And now I just replace all the G's by variables. And I have a system of equations that has, it's not quite of that form, but it's similar to that. And I get a system of equations which has the solution G1 through GK. But the same system of equations also has the solution every yi equals the identity. Right? Because if I stick the identity in place of n, this all becomes the identity, and I get some solution there too. So I get two possible solutions. So all you have to do now, once again, is to take that system of equations the way I've written it and play with it for a while to see that you can find a similar system of equations of this form, which has the same solution sets. And so that's all doable. So this is a complete characterization, and in particular that tells you that if a group is algebraically closed, subgroups which are normally generated and satisfy this property just don't exist. Right? They're trivial. Now think about what that means for a minute. We can say when a finite group is closed. So there's another example. G finite, then G closed if and only if G nilpotent. Right? Why? Well, it's finite. So gamma k of G equals gamma k plus 1 of G for some k. There's some k at which I mean, you can't have an infinite descending sequence of proper subgroups in a finite group. So eventually they've got to stabilize. And gamma k plus 1 of G equals G gamma k of G. But this is gamma k of G. So, and it's a finite group. So this is in fact generated by a finite number of elements. It's not just finitely normally generated. So that implies that gamma k of G is 1. Which of course implies that G is nilpotent. And of course we've already shown that nilpotent groups are closed. So finite groups are closed if and only if they're nilpotent. Well, let's just say a little bit more about closure, and then we'll move on, okay? So here's a fact. It's not hard to prove. The class of closed groups, it's going to be slightly awkward the way it's stated. The class of all groups which are algebraically closed is closed under the following operations. Is closed under limits over small categories. Now, whether or not that sort of categorical nonsense makes sense to you or not, there are very simple examples I can, just to make sure you understand what I'm saying. Products. Right? Examples of that, products of closed groups are closed. Kernels between closed groups are closed. Pullbacks. Inverse limits. Intersections. Those are all examples of operations you can do on closed groups and get more closed groups. A lot of those are, I mean, for example, pullbacks and intersections are examples of inverse limits. So are kernels, I guess. I mean, a lot of those are the same thing. They're all, in fact, in some sense, examples of inverse limits. They're all examples of limits over small categories, right? So that gives lots of ways of constructing interesting closed groups. So this has the corollary that the pro-finite completion, or pro-nilpotent completion of closed groups is closed. Because as we showed initially, that's the inverse limit over the nilpotent quotients, the quotients by the lower central series. Right? So in fact, the nilpotent completion of any group is a closed group. And another observation, and this will be, I think, the last one I want to make before we move on, is that given a map G to gamma, gamma closed, G has a unique closure in gamma, i.e. a smallest closed subgroup. Containing the, let's say it's called that phi, containing the image of G. Right. So let's just see why that's true. It's probably clear, but always good to write down a proof, however easy. So why? It's the usual thing you do, right? You let, let S equal the set of H such that H is closed. H is contained in, and phi of G is contained in H is contained in gamma. And that's non-empty because in fact gamma is an S. Right? It's non-empty. So you take, so the closure is the intersection for all H and S of H, and that's some subgroup of gamma. Right? That clearly is a closed subgroup because intersections of closed groups are closed. And it's clearly the smallest one, so it has a closure. So maybe we look at an example again. For instance, let's go back to the infinite dihedral group. Okay, so let's call that G. Maybe we'll call it D for dihedral, the infinite dihedral group. Then we computed D hat, and that was the two adic integers, semi-direct product Z2. Right. Well, I'm not going to show you, and I'm not going to prove for you, but a little something you think about, maybe you can take as an exercise, is that the closure of D in D hat is the following. So inside the two adic integers, you can find the integers localized at 2 as a subgroup. You might think of it this way. The two adic integers you can think of as power series with coefficients in Z mod 2. And you take the rational functions in those power series. And that gives you Z localized at 2. So in particular is Z localized at 2, semi-direct product Z2, contained in the two adics, semi-direct product Z2. And Z localized at 2 is just the set of P over Q in the rational numbers where Q and 2 are relatively prime. Okay? So there's some, you can see you get something that's somehow bigger than the original group usually, but much, big enough to be closed, but much smaller than the completion. It's no longer uncountable. Now, before I state what Jerry Levine's big theorem is, I want to talk about one other interesting thing related to this. And it's a very old conjecture of Baum's log. So let's see. A group G is para-free if a finitely generated group, para-free group will be a finitely generated group if there exists a homomorphism F to G, this is a free group, such that F mod gamma K of F is isomorphic to G mod gamma K of G for all K, and the intersection over all K of gamma K of G is the trivial group. Okay. And that's equivalent, let's say it slightly differently, which maybe is a little more, little easier to understand. Equivalently, it says that if I take the map, it says that f hat is isomorphic to g hat via that map, and the map g to g hat is 1-to-1. Right? Because the intersection of the map from G into the inverse limit of the lower central series quotients is the intersection of the lower central series. So that's a nice way, very nice way to characterize it that's consistent with the things we're thinking about as we think about Milnor's invariants. So it turns out that there are tons of these. Gilbert Baum's showed that this is due to Baum's log. So maybe I'll put his name here. And Gilbert showed tons of these things exist, and infinitely many classes of such things exist. So it seems like it's a very complicated collection of groups. And he conjectured the following. Baum's log's conjecture if G is pair-free, then the second homology of G, that is by definition the same as the second homology of the Eilenberg-MacLane space, KG1, is 0. It's remarkable. This was conjectured back in the 60s. I mean, I can tell you that I have spent thousands of hours thinking about this problem. And I suspect that Roman would tell you that he has, and I suspect Gilbert has, and I suspect that there are just a lot of people who've thought about this problem. This problem appears to be closely related to all sorts of questions, including whether or not there are transfinite Milnor invariances. We'll see. It's related, I think it's related to the, I believe, although the evidence is slim, I believe it's closely related to the disk embedding theorem in dimension 4, the Friedman's disk embedding conjecture. Whether or not you can classify 4 manifolds via classical surgery theory for all groups, topological 4 manifolds, as you can, whether or not that works in low dimensions the way it does in high dimensions, I think will ultimately be related to the resolution of this theorem, of this conjecture. I'm sure that many people who are experts in that subject would tell me, that that's ridiculous, but I believe that. And it certainly is related to lots of interesting questions about 3 manifolds and knots and links. And it seems to be incredibly hard. And let me make clear, I don't think there's a shred of evidence for it being true. I mean, no evidence. Except that nobody can find a counterexample. Right? Nobody can find a counterexample. Okay. Here's a fact that if G is finitely presented, sorry, I meant to define something and I failed. Let me just make clear, okay? Let's denote notation. Let's denote the closure of G in G hat by G bar, okay? So G bar is the closure of the image of G in its nilpotent completion, okay? And then and then here's a fact that Levine observed. If G is finitely presented, then G bar is a limit of groups HK, where HK is finitely presented. Is finitely generated. I just need generated here. Is finitely generated. Now that has the following corollary. If H2 of F bar is non-zero, then the pair-free conjecture is false. Because homology commutes with direct limits. And G bar F, so F bar is the direct limit of groups, which are parafree groups, actually. They'll be parafree groups. I didn't say that here, but these will be parafree groups if F is for the free group. And right, F bar implies the HK are parafree. And the only way the homology of F bar could be non-zero is if the homology of one of the HKs is non-zero. So that would be a parafree group with non-trivial second homology. So that indicates that this question about computing the homology of these groups F bar seems to be very hard and very deep, in the sense that it's related to a long, old classical problem which has been given a lot of attention. Nonetheless, the things I'll talk about certainly indicate that there may be ways of finding counterexamples, and we may be heading towards finding counterexamples to the parafree conjecture. Now, let's see where I am and what I want to say. So let's just state a problem. An important problem, I think, is compute the homology of F bar. Right? I think that would be a very nice thing for someone to figure out how to do. Okay, so what did Levene prove? Levene developed this notion of algebraic closure. Why did he develop it? Well, he was trying to realize or see what we could say about this invariant this invariant theta omega. That was the reason he first looked at the notion of closure. And he proved a theorem. I'll only state part of this theorem. He proved that given G, there exists a group that you would call the algebraic closure. Of G. Let's denote that. We'll denote that as EG. And a natural homomorphism G2EG satisfying such that the following is true. Given any map from G, they have the map from G to EG. Given any map from G to another group where this is closed, there exists a unique map EG to gamma, making this commute. So given a phi, there's some phi bar. Okay? So it's the initial algebraically closed group, right? It's the initial algebraically closed group. I think it's implicit here that this is, in particular, an algebraically closed group. It's the initial algebraically closed group G maps to. 2. If G to gamma is a homomorphism such that the following is true, G abelionized is isomorphic to gamma abelionized. That is, if I mod out by the commutator subgroup, they're isomorphic. And H2 of G is onto H2 of gamma is onto, and G in gamma finitely presented. Then EG to E gamma is an isomorphism. So it localizes with respect to the class of maps between finitely presented groups, which are isomorphisms on abelionization and onto second homology. Okay? Turns those things into equivalences. And the third thing, I'll mention 4 things here. This isn't everything he proved, but it's certainly part of it. The map EG, in particular, right? In particular, right? If I put G hat here, that's an algebraically closed group, so I get a map from EG to G hat. And if I take the image, that's in fact G bar. It's the closure of G in G hat. And finally, given G to H finitely presented, finitely generated is enough. And G abelianized onto H abelianized, then EG is onto EH. The closure of G maps onto the closure of H. Now let's put those facts together and see what it says about links and transfinite Milnor invariants. So I start with L and S3 with all the mu bar invariants of L identically 0. That means the longitudes of the link line the intersection of the lower central series of its group. Right? Then I have the map from meridians into pi, by that I mean pi 1 of the exterior. And this gives an isomorphism after, gives an isomorphism after I take localization. And so I get, after I take the nilpotent completion, so recall I get this map from EL. So I have a map from F to EL to KF hat. Well, let's just do groups. F to pi to F hat. Right? And this map is just, this composition is just the nilpotent map, the inclusion into the nilpotent completion. Okay? Now, I also have this map from pi to E pi. And I have this map from F to EF. But this map is an isomorphism on abelianization, right? Because the first homology of the group is the first homology of the exterior of the link. And that's generated by the meridians. And this is generated by the meridians. So this is an isomorphism on abelianization. So by the last statement, this is onto. On the other hand, I have this map. Well, on the other hand, over here, I have F bar. And that's contained in here. That's the closure inside the nilpotent completion. And the image, I have the map from the group closure of the free group. I can map, this is a closed group, so there's a map from here into here, and its image is F hat, F bar rather. But wait, I have a map from pi to F hat, and this is the closure of pi. So I also get a map like this. But because this is onto, these two maps have the same image. And so so this factors. So let's see. So I get a factors. So pi into F hat factors through F bar. Right? I get this factors. Right? So why is that worth anything to me? Well, I can now try to define the invariant using F bar instead of F hat. My transfinite Milnor invariant I can refine now. So I have EL, but now I actually have a map there into KF bar 1. And then that can go on to KF hat 1. Okay? So I have that map into KF hat bar. And in here I have the boundary, which is L cross S1. And in here I have the wedge of circles, which gets mapped by the identity to the wedge of circles in here. And now I have, and this map is just projection onto the wedge of circles. And so I get this map S3 into K F bar 1, union over a wedge of circles with a wedge of disks, into K F hat 1, union over a wedge of circles with a wedge of disks. This is what I call K omega, and we'll call this K infinity. Just give it another name. Okay. So that tells me that I have this invariant theta infinity of L in pi 3 of K infinity. And I have theta omega of L in pi 3 of K omega. And I have this map, and it takes one to the other. So Levine proved the following. Theta omega in pi 3 of K infinity is a concordance invariant. And the following things are true. Well, let's see. For any x in pi 3 of K infinity, there exists some link with theta infinity of L equal x. So if we knew this group was non-zero, we would have a transfinite Milnor invariant. Okay. Unfortunately, we don't know that. But we have this other space, pi 3 of K omega, we know is huge. So for the first time, we have some hope of detecting things in pi 3 of K infinity. We didn't have that hope before. For the first time, we have some hope of seeing things there. And 2, theta infinity of L, this is just done exactly the same way, with one modification, the same one needed to prove this. It's done along the same lines as the way we proved this, the analogous result for the finite invariance. Theta infinity of L is 0 if and only if there exists connected surfaces, disjoint connected surfaces say Fi in D4 with the boundary of the Fi equal to the link in S3, and such that if I take pi 1 of the exterior of these surfaces and I mod out by gamma k of pi 1 of the exterior of the surfaces, that's isomorphic to the free nilpotent quotients for all k. That is, the group of the exterior of those surfaces has the same completion as the free group. So this says that those surfaces aren't disks necessarily, but they look like disks to the lower central series. So it really is a type of slicing type approximation. It sees very clearly where this happens. Now the proof is, well, you do exactly what we did before. You take the center points of these disks. You take the center point of these disks, here it is, and you pull them back. And that gives you a link, but the components aren't connected. Unfortunately, it's still not the case that the exterior of that link maps onto this group. Maps onto, I wanted to put bar here, right? You do, don't I have a diagram here with bar? Oh, here it is. Thank you. Yeah. So unfortunately, it's not true that the exterior of that link, which doesn't have connected opponents, maps onto F bar. But it turns out that the elements you need in order to connect it up are sufficiently small in some sense that I can change that. I can change the group. I can change the group of the three manifold by a homology cobordism, or by a concordance actually of the link by a concordance, so that then the new link, which is concordant to the original one, maps onto not only the free group but also the elements I need to connect things up with. Right? So I can then do the same argument I did before. So the key idea was that this idea of F bar tells you how much the image of a link complement can change under homology cobordism inside the nilpotent completion of F. It's answering the question, a partial answer, suitable enough for this problem, how does the fundamental group of a three manifold change under homology cobordism? Okay. So that's how you prove both the realization and also the geometric interpretation. So now we can ask some obvious questions. So here are some problems. Is pi 3 of k infinity non-zero? Okay. Seems to be very hard to compute, but we have some hope of computing something now, because we can compare it to elements in something we know is huge. There's a map from this to something big we can use to detect elements. So note that if I take pi 3 of k infinity, that there's in fact a Hurwitz map. The Hurwitz, I should know how to spell that. Hurwitz homomorphism. I hope I spelled that right. Onto h3 of k infinity, and you compute h3 infinity as h3 of f bar. So you can ask, is h3 of f bar non-zero? If it is, then we have transfinite Milnor invariants. And so that's one question. There's another one. And a third one is, what is the image of pi 3 of k infinity into pi 3 of k omega? Okay. In particular, are the elements in pi 3 of k omega that Roman and I compute in the image of pi 3 of k infinity. If they are, then in fact we've realized, not only have we realized Milnor's a transfinite Milnor invariance, but that will solve the pair-free problem, the pair-free conjecture, give a counterexample of the pair-free conjecture. And I should comment that, this might be, at this point, no one has any idea how to go about solving the pair-free conjecture. This might be the best avenue, the best hope of a solution that exists right now. It's the only hope for a solution that I can tell that anybody has right now. It's progress that people haven't had. Now, so again, that would be a theorem that I have it in my notes to state, but I'll just leave it as an unstated theorem that of Roman and I, that maybe I stated it earlier, that if the image is non-zero, then the pair-free conjecture is false. Okay, now I want to finish up by talking a little bit about homology cobordism and how one can define analogous invariants, sort of transfinite Milnor invariants, to understand homology cobordism of three manifolds, and and that they're realizable, to give you some evidence that transfinite Miller invariants may well exist. Okay, so that'll end it up. So homology cobordism. So we talked about this already, but let me remind you, M is homology cobordism to M, say M0 to M1 if there exists a four-manifold W such that the boundary of W equals M. These are oriented three manifolds, disjoint negative, the M1 with the opposite orientation, and the homology of W Mi is isomorphic to 0 for I equals 0 and 1. So that just says it looks like a product homologically. Okay? Right. So we've done this picture before, but let me remind you. Right, you've got this manifold W between M1 and some manifold M0, and this looks like a product. To homology theory. Now, all the invariants we have, all the invariants I've talked about for concordance of links, all of them are actually invariants of homology cobordism of the exteriors. Every one of them. Okay? Every one of them. So anything I've talked about is an invariant of homology cobordism of the exterior. So in a sense, everything we've done has really been questions about getting invariants of homology cobordism. Now recall that if x to y is a homology equivalence, it's an isomorphism on homology, well then in particular if I take pi 1 of x and I abelianize it, that's the same as pi 1 of y abelianized, because the first homology of a space and its group are the same. And h2 of pi 1 of x and h2 of pi 1 of y is onto. Right? So why is that true? Well, because I can get the space, right, because the homology of the second homology of the group, or the homology of the group, is the homology of a k pi 1 complex. And I can take any space with fundamental group x, and I can change it to a k pi 1 complex by adding cells of dimension greater than or equal to 3. I add 3 cells to kill pi 2, I add 4 cells to kill pi 3, and I just do that transfinitely, right? So I kill all the higher homotopy groups and I get a k pi 1. Well, if I'm adding cells of dimension greater than or equal to 3, I don't change h1, and h2 can get smaller. What happens after that, I can't control. But h2 might be a quotient. And so this turns out, because this is an isomorphism on h2, this is onto h2. So that implies, by Levine, that implies, right, that e pi 1 of x is isomorphic to the closure of pi 1 of x is isomorphic to the closure of pi 1 of y. In particular, right? In particular, if M naught is homology cobordant to M1 by, say, some W, well, all three, M naught, M1, and M and W, all have the same homology. Right? They're homology equivalent. So then E pi 1 of M naught, the closure of pi 1 of M naught, is the closure of pi 1 of M1, and that's the closure of pi 1 of W. So given a three-manifold M oriented, right, compact, I guess, or closed, right, there exists a map M into K pi 1 of M 1. And I can take the homology class of M, the fundamental class of M, and H3 of E pi 1, or E pi. E pi 1 of M. If I got enough there. I can take that homology class. And then one can define, yeah. So that's a theorem. Let's state a theorem. Almost done here. All right. So this theorem is due to Jae-Chun Cha and myself. And it says, given M is above, there exists a well-defined homology cobordism invariant M in H3 of E pi 1 of M. Unfortunately, if I just take that, it's not well defined. So I have to mod out by the automorphism group of E pi 1 of M. Right? Because this depends on some identification of the group of the group with pi 1 of M. Right? Of the closure of the group with pi 1 of M. And under homology cobordism, I have different identifications of the group. So I have to mod out by this. Well, let's just leave it at, I guess, let's see, is there anything else I want to say? Let's leave it at that. So that's a type of, so a little note, a type of, if you like, transfinite Milnor invariant. For homology cobordism. Of three manifolds. Now let me tell you, we could say more. Let me describe another theorem. To do so, let me just describe a group for you, an example. So, let G be the group UST, where U inverse equals S inverse, U inverse equals T inverse, and S and T commute. Okay? And if I kill S and T, I just get a copy of Z. So this maps onto Z. And the kernel is generated by S and normally generated by S and T, but U acts trivially on S and acts by negation on both S and T. So in fact, the kernel is generated by S and T, and they commute. So the kernel is Z squared, and since Z is free, it splits. I get a semi-direct product. So here, this is U, and this is generated by S and T. And here, U is acting on the generators here by negation. Okay, and then here's a theorem. This is Cha and myself. Ought E of Z squared semi-direct product Z acts trivially on H3 of E of Z squared semi-direct product Z modulo the action of negation. Right? And for any element, well, and H3 of E z squared semi-direct product z is isomorphic to z localized at 2 mod z plus z. So you can actually compute it. The realizable invariants are the set of things of the form x1, where x is in z localized at 2 mod z. In this decomposition, it turns out you'll always go to 1 or negative 1 up to sine 1. And anything of the form z, and anything in z localized at 2 mod z can be realized as an invariant. And so that has the corollary that there are infinitely many. So let's see. So in particular, so that has a corollary. So notice that z squared semi-direct product z is actually pi 1 of a 3 manifold, where M is a torus bundle. Over S1, right? I just take S1 cross I, and I glue it to itself by the negative map on each sum end, and that's an orientable manifold. It's an orientable 3 manifold because it's negative on both sum ends. It's an orientation-preserving homeomorphism of the torus. And so that's an orientable 3 manifold. And so this has the corollary that there exists infinitely many homology cobordism classes of 3 manifolds homology equivalent, with the same homology, let's say, with the same homology. Actually, they are homology equivalent. Homology equivalent to M. And you can say more. I'll just state this as a note, but it should probably be stated as part of the theorem. These manifolds have the same group closure and the same cohomology ring. As M as well, right? That they're all different homology cobordism classes. Now let me state one more theorem, just to tie it in. I want to tie this in quickly with and then I'm done. I know I'm going a little over, but I want to tie this in quickly with the colloquium I gave the other day. In the colloquium the other day, I talked about using Cheeger-Gromov row invariants in the L2 signature theorem, using L2 signatures of 4 manifolds to find homology cobordism classes of manifolds in a given homology type. If you combine this, combining with the results of the results from the colloquium, we get the following theorem. Cha-or, right? On the L2 signatures, right? The amenable signature theorem, we called it. Then there exists for any realizable homology class in H3 of E of z squared semi-direct product z modulo the action of positive or negative 1, right? That's where the invariant lived. right? There exist infinitely many 3 manifolds with homology equivalent to M. Well, with the same homology as M. Let's be careful. And distinct, pairwise distinct homology cobordism classes. So said differently, right? Give the class of 3 manifolds with the homology groups of that 3 manifold, of that torus bundle, right? I have a map to this collection of invariants. For each invariant, I have a whole orbit of collections of things with that invariant, which are an infinite number of distinct homology cobordism classes too, right? So that's where I'll stop. Thank you.